I hope this lecture will be interesting, and this is the plan. First of all, I need to admit that I'm really bad with title creation because this title is not very informative. Today, I will give you more of an introduction to the cosmological simulations that we use in computer simulation that we use in cosmology, mainly most large structure. I will start a little bit of the something background and a bit of history, which I think is important to understand when was the turning point when everyone in the field started taking this thing seriously. Now, many, many years later, we know this is like a very essential tool to understand the universe, and it's a very useful tool. But nonetheless, it not always was like this. After the history, I will give you some crash course on the fundamentals, and we're gonna stick to the gravity on the simulation because just to do hydrodynamics, which is actually now very well developed field, will require a completely separated school. Nonetheless, gravity itself, you will see, it's already complicated if you want to solve it in a setup in cosmology. And finally, I'll tell you something about what you can do with the raw output of a simulation like that. Now, this will prepare the stage for Friday, when in the morning, I will show you the test case, how you can actually sit down and think about hard questions that you have for the universe and use in a very smart way simulation to test some hypotheses or even stress test models of dark matter. This will be Friday morning, and this will be like a test case that I hope will be just a nice example how you, from the first principle of questions you might have, you might design a simulation to try to answer this question and help you get informed better. And in the second lecture session on Friday morning, will be around noon, we'll have live sessions. So it wasn't possible, unfortunately, to create workshop because you attended so nicely. So many people attended the school, and I'm only one. Unfortunately, we cannot make a workshop for 70 people. But the next best things we can do is that I will try to show you in a live session some simple things and hacks and approaches to running simple simulation, taking something, designing, looking at the parameter files, compiling some stuff, hopefully doing some nice simple plots, and we're learning something. I think this will be very useful for all of you that never run computer simulations before. And for those of you that were running them routinely, maybe you will learn also something new because I will have a few tricks under my sleeve. Okay, that's the promise. So today, setting the background and introduction to basic methods, concepts of the computer simulations. With some physics as well. Friday, much more science and hopefully fun with the live session in the second part. Okay, and of course, just like John previously said, I will really welcome questions when they go on the fly. So if something is not clear, if something brings your attention, just don't hesitate to put your hands up, interrupt me. Actually, I would like to say that enjoy interruptions because it means it's not one way, right? I think there will be something that at least somebody is listening to me. Maybe I know, maybe I have some Easter eggs for you to pick up. I don't know. Let's see. Okay, let's go. Hopefully we can do it today, and we'll all survive and learn something. So this lecture course, actually, some of the slides and ideas for slides are borrowed and based from some of the people I enjoy working and learning from over the years. They're listed over here: Carlos Frank, Walter Springer, Adrian Jenkins, Alex Kneve. But I also prepared some small lecture notes this is a version from Cosmology School number 3, I think. You can access them on this link. Later, of course, if you need, we can also, I will share the slides definitely. We'll make available slides for you online, so you can click the link. The lecture notes are basically, more condensed, more mathematically rigorous the explanation of some of the things I'll be covering today. Okay, there's also some useful references. I mean, this is not a full course, because this will take like 40 hours, so like 30 units, right, to at least cover the things with the sufficient level of details. Nonetheless, if you're interested in the subject, something you would like to deepen a bit the knowledge and make yourself more familiar with some of the more advanced topics related to simulations, there are some nice list of references for you that you can follow. It's of course not complete, and maybe also I take the blame not up to date. Some of the older codes you can see here now we have like gadget 1, gadget 2, that's completely vintage codes now. Nonetheless, it's a good starting point for you. All right, let's move away from all these technicalities, all the things I wanted to say. Not all the things. This last but not least from introduction, I'm really happy for the organizers for giving this opportunity, for inviting me here and asking me to deliver these lectures. And I think this is amazing, well-organized school and meeting that we all can take example from. So big hats from our heads for them. All right, computer simulations. First of all, it's not only about pretty pictures or movies. This is something that we see at the end, and it's not bad to make good pictures and movies. First of all, it's not only good because they look nice, but simulations and the results, if we use visualization of the results of cosmological simulations, can give us a nice physical intuition what is actually happening. Especially what is happening when the structure formation becomes nonlinear, violent, things are clustering, collapsing, orbits are crossing, and if you have a hydro, the stars are forming, there's a feedback mechanism. So, just playing the movies, we're just humans. We like stories. We like to understand things also, especially. Give them at least some understanding, good intuition. One thing is you can look at the equation and understand how to solve the equation. The other thing is to visualize, okay, this equation describes actually this process. This is how galaxies form. This is like halos merge together to make bigger halos. So this means that these pictures and movies can be also very useful. Nonetheless, they also provide us with very good visuals. But most important merit in cosmological simulations of structure formation is actually to try to understand and model and study numerically the process of the growth of structures on the cosmic scale. So we start with the beginning of time. We don't go as far as like that. It will be a Big Bang. So next information we have really is the cosmic microwave background radiation, and this you will see usually is the basic starting point for us. And then we try to understand from this initial conditions, this picture of the cosmos. You heard a lot about the CMB today and yesterday from Peacock, but also in the previous lecture. The CMB is nice because the physics is relatively simple, it's linear regime, and provides us with a very nice statistical description of how the cosmic density and velocity field was like when the universe was very young. And this is starting point for us. But this is the big problem we have in our hand, because now we need to model evolution of 14 billions of years of the density field, whether the density fluctuations arose from 10 to minus 5, as we see here in the CMB, to an order of unity or millions if you go to the centers of galaxy clusters or galaxies when it comes to dark matter. So it's a huge dynamical scale, 11 or 12 orders of magnitude to follow in density. So this means it's a very, very hard problem. And definitely as soon as we hit so-called non-linear regime, things usually go over the board, and that's why the simulations are very useful. Usually you do this like that. You take the CMB, you take some supercomputer with trained personnel to operate the supercomputer, as an example of a trained personnel over there in the picture, and hopefully this personnel in the picture haven't managed to break a single supercomputer yet, although I try, trust me. So also advice for you, if you start to play with simulations in the future or now, don't be afraid that we break down supercomputer. It's very hard. I mean, they break down themselves because of entropy, not because of your calculations. So we use the supercomputers as a help and try to understand the process of structure formation. And this supercomputer simulations implement the laws of physics, all the laws of physics we think are relevant for the given process model. And I will mostly focus on the gravity, and it wasn't even going to be GR, as you will see. And as soon as we start adding more complicated laws of physics, then of course the simulation also becomes more complicated. And of course, the simulation computes how this primordial fluctuation grew and became modern galaxies. And if you do everything right, you hopefully obtain a picture like that. This is on the x-axis is the time line, and on the y-axis you have a density rendering of the dark matter fluid from the early times. At the left hand you will be probably reaching around 1000, well maybe 100, and on the right hand side you arrive at which is yours. So kind of a time. You see, this is how emerging of the logical structure, acoustic web, about which you heard in the last week from Lingua and the Viper, for example. And this is from rendering from P-millennium simulation. P-millennium is not from Planck millennium, maybe some more details later about that. Okay, so we start with the recipe of the universe. We have the standard model of cosmology, of course, that we love or hate and despise. I think we should be very proud of it. It's a very proud, huge achievement of the humankind that we, knowing all the laws of physics we know, plus a few simple numbers, parameters, allow us to build a model of the whole universe and its history. And it's actually a very successful model, right? It passes tremendous amount of the observational tests. Nonetheless, of course, there are cracks under the hood. You've seen some observations are not fully compatible. There are definitely physics that is missing. We still don't know what the dark matter particle is. By the way, more about this on Friday. So bear in mind that this is our best current understanding of the cosmology, but it's no way the final answer, for sure. So if you want to do some more stuff in the cosmology, this is one of the best times to do this, because most exciting. Because the computer power is there, the observations will come here, and I'm pretty sure we're going to discover so many interesting things, and there's so much more to do now. I'm a little bit even envy that I was younger. But nonetheless, we have these parameters that describe standard model, and you can easily fit them on one sheet of paper, one table. Depending if you want to be very conservative, you can even get away with 6 numbers. That's a classical vanilla number CDM. And there's some more derived parameters if you want to be a bit more specific. Yet, you need probably hundreds and thousands of pages of many books to try to describe all the complex structures we see in the modern universe. So we start with some simple universe. We can summarize it statistically by just 6 numbers and some simple laws of physics. And yet we observe some complicated structures today that will take much more information to just describe and even understand. Why? Well, the answer is gravitational instability. That's the main driving mechanism in the universe, as far as we understand this, that brings the early primordial universe fluctuations that are very tiny, and given the time, because gravity is very patient for us, in expanding background, it creates all these magnificent structures. And later, of course, if you do bionic physics chemistry, from CMB and fluctuation to people, flowers, birds as well. But of course, we put people, flowers, and birds aside, which is focused on gravity today. And as soon as this gravity hits into nominal regime, things become complicated. And that's why you have this variety of observed structures. So I would summarize the goal of computational cosmology, which is basically a field in which we extensively use computer simulations to understand, model the universe, to understand the physics, and also model the observations, will be the following. We start from the CMB, when the universe is young, and nearly smooth and homogeneous. Right? Homogeneous.
Wrong.
Wrong.
Homogeneous.
Homogeneous. Okay, homogeneous. Thank you very much. Yeah, that's the most important point. Well, very smooth. Basically, it means that whenever you put it's invariant under the shift translation, more or less everywhere. Everywhere has similar properties, and also, by the way, isotropic, which you know from CMB. Then we have gravitational instability that drives the structure formation. And now, see, the initial conditions for the universe are known. We have CMB. I mean, put aside if there's something in the CMB that we don't understand. At least we understand we can derive very precisely the spectrum of the distribution of the fluctuation on what scales, power spectrum. And they also look very adiabatic and Gaussian. So we can use this to basically make many copies in simulation and ensemble averages of the universe with the different phases, as long as they fulfill the same initial power spectrum. So since the initial conditions are known, understanding global structure in our universe is a well-defined problem. However, it's a difficult problem because the gravity is inherently non-linear, and the physics is complicated, and the rich hierarchy of all the structures resists a simple one computational framing. But in principle, we have a solvable problem on our hands. So of course, this means we'll many approaches to do this. and we're still developing this, and we will see the problems, but in principle, in the best case scenario, it would be just problem of the nearly infinite computer power to really go to all the level of details you would need. In practicality, you will never get that amount of computational power, and there also will be problems with cosmic variance and amount of information. Nonetheless, it should be solvable. So the simulations are crucial. Why? Because they give insights into the structure, formation, and galaxy evolution process. And we know, well, we can try to understand physics better and try to then connect the understanding we get from simulation with the physics and then with observations, of course. This is the most important. Remember, simulation is the only tool. They never create a real universe. They never a real answer. They're just a simple tool that help us understand things better. But also, this tool is not only for understanding better physics, but this is the best thing we have now in cosmology that resembles controlled sample experiment, right? Sometimes I could say I really envy our particle physics colleagues. I really don't probably. Because they have CERN, they have Large Hadron Collider, they can do another colliders, and they can really smash the particles, control everything, energy, average, magnetic fields, whatever they want, and they do billions of repetitions, and they can really just collect whatever comes out, and then they learn. Amazing. Well, of course, we cannot go out there to the universe, to the space, and make galaxies collide, obviously. So actually, we study the universe. There's only one universe to study, and we're actually inside of this universe, and it's very hard. And we also have limited amount of information because time, the light travels with a limited velocity. So of course, the further we look, the earlier we see. So it's a complicated thing. So since we don't have a chance to do real control sample experiment, the computer simulations are the next best thing we can come up. It's kind of like a forensic evidence in the court case. You build a court case, you want to find a culprit or proof. Okay, dark matter, it's called dark matter. This is responsible for the properties of galaxies within the small space. That's your hypothesis, and then you build forensic evidence using simulations, for example, playing around with the dark matter model and its properties to see what happens, and of course at the end you try always compare with the evidence, which is the real observations. So the simulations allow us also for model testing, provided the physics of the model test can be implemented in some way in the engine of the computer simulation for structure formation. All right, but it's also about pretty movies. I will show you this short animation made by my colleague Rob Crane from James Moore University in Liverpool. This is from one of the early stages of the Eagle simulation for galaxy formation. This will be about rendering what happens if you have dark matter, gas, stars, supermassive black holes, everything we know, and you actually can model in simulation. This will be state of the art. We won't going to cover all these extra nice schemes for the gas and galaxies, but nonetheless, you can see what is the. Hopefully, I will be able to launch it on here. So we start to see at redshift 15, the time flies t is time from the Big Bang. Size of the box is only 25 moving megaparsec. And of course, the universe does not rotate. What rotates is a camera. It's our vintage phone. But you see, as the gas really follows we don't render dark matter here, but gas really follows the gravity and the gravity of dark matter and start to, follow, condense into the halos and galaxies. As soon as galaxies start to form stars, you have this explosion. From time to time, it's just energetic feedback because some of the galaxies form stars in the process we know called starburst. In a very short time, huge amount of energy is ejected to the intergalactic medium back because of the supernova. Because if you form stars rapidly, many of the stars will be very massive, and massive stars will be very short. And it's called so and so forth. This is for astrophysics. But nonetheless, you see this way looks nice. Although you have to bear in mind that this is a false picture, not because it's a simulation, because we do simulation in moving coordinates, and the real universe has a physical coordinates. So this box looks like it's a constant thing, right? We look one time and nothing happens, just things condense. But in reality, this box has changed its physical size, all the physical distances inside the simulation, from the early times to the late times by 30, because we started mentioning 20, I think, in the movie, something like that. So this book was tiny physically, it was growing, it was universe expanding. So bear in mind that these movies look nice, but at the same time the things are condensing, the universe is expanding. So things are a bit more complicated. All right, let me go back here. Okay, so before we go to the nitty-gritty details, which probably will bring us to the time after the coffee break, so hopefully we'll have us survive some technical details about how we approach to solve the gravity simulation. I want to give you a very short passage about the history of the field. Of course, don't worry, not going to go that far like in medieval times to Abacus. As the available computational power grew from 70s to 80s, more things could be done. And I will show you some of the results from very many simulations that have thousands of particles, many thousands of particles. You'll see nowadays we use trillions of particles for computers to model the density, phase space density. So there were random computers that were probably much less powerful than the very cheap made calculator these days you can buy. Let's say programmable calculator. Nonetheless, this piece of history will be important because I think it will show you how we have witness of huge landslide in our approach to simulation in the 80s. How from something that nobody will believe that can be really followed usefully, we went from a field that was very premature, very simplistic, to a field that actually allowed for hypothesis testing and model falsification. So okay, this start goes back from the 70s, where there was this approach, a bit of the discussion between West and East of how the structures form in the universe. What we know is gravitational instability, but the question was, is the structure forming from top to down? Means first we form the larger structure, superclusters, then kind of a big filaments, and only later they fragment to smaller pieces, and from the smaller pieces you have condensed to galaxies. This was the top-bottom approach promoted by most Soviet scientists, and the star of this was Yakov Borisovich, who, by the way, apparently is attributed to this quotation when he said about the gravitational instability, that the theory of formation plus the structure, the gravitational instability mechanism is much alike to capitalism. In due time, the rich get richer and the poor get poorer. The gap between rich and poor grows continuously and finally becomes catastrophically large. And of course, it has a little bit of appealing in the 70s in the Soviet Union, although I also thought that he ran into trouble when this information went back to KGB. Said, how can you say the universe is like capitalism? But of course, he went away with that saying, no, look, it's catastrophically bad like capitalism. So apparently, he get away with that. And actually, they had a nice support of the ideas, and they were starting doing, the group of Zeldovich in Moscow University, very simple simulations. These were simulations that were actually conducting one-step calculations. Later, we will cover them. It's called Zeldovich approximation. There was a very influential paper by Zeldovich, and he thought basically he cracked down the problem of structural formation in the universe, doing only Lagrangian perturbation theory. But basically, here you still need to visualize the results. And this is the plot from the paper, review paper about this field by Dorostkevich, Zeldovich, and Sunayev from 1976. I got this plot from my friend Sergei Shandarin. By the way, that's why he put the caption says the figure is made by Sergei Shandarin. And interestingly, back then, the printers, at least in the East, were only alphanumeric, so they couldn't put enough dots close together. So whenever the capacity of the dots per inch, or whatever, square inch, is exceeded, then the printer gives you a number. That's why, it's like a Minesweeper project. That's why, when you have dots, and whenever there should be 2 dots, you have a number 2, 3 dots, number 3, and 4. You see, it's actually looking like you have some kind of a filaments and maybe kind of a pancake planar structure wrapped around. And this is the outcome of Zeldovich approximation if you start from some arbitrary scale-free initial power spectrum. Now, in the same time in the West, The first very meaningful structure formations simulation came from the small scales. In the West, was Jim Peebles and the school of many others as well, when the belief was that the structure in the universe arose due hierarchical process from bottom up. So it means first the smallest things condense and collapse, and only by sequentially merging of smaller things to bigger things, small halos merge together, small galaxies cannibalize themselves and grow to bigger galaxies. You eventually get to the point when you see large-scale structures we observe today. And that's why one of the first interesting simulations was cluster simulation, and it started with kind of a collapse of the over density. And back then, later, we had the Einstein Observatory. That was one of the first of the X-ray observatories in orbit. And interestingly, whatever is this simple simulation of clusters gets you kind of a profile, or kind of interestingly, given the big error bars, matching the cluster X-ray images from early on. So at least, they had some hint in this respect. Later, there was RSET, famous first N-body code that was also made public. And they also run simple simulation of structure formation. They start with some scale-free white noise power spectrum. The ranges are really arbitrary. This is important because this is the area when there was CMB. There was only known dipole with CMB. There was no CMB fluctuation maps back then yet. So people back then didn't know what were the initial conditions for the universe. They had to guess and then try to see, okay, we put this kind of fluctuation, we see what happens after that many evolutional dynamical time steps. Not that many redshifts or that many billion years. The scaling was quite arbitrary. Nonetheless, they got something interesting, like after 15 dynamical times, redshift 40 to 0, they obtained some finite clustering. And then the story changes a bit when we have something that was later called Gang of Four. It's a famous group of computational cosmologists that assembled in Berkeley under command of Mark Davis. So we have George Estappo, Simon White, and Carlos Frank. And they were happy enough to get their hands on the newly purchased by the Berkeley University, California computer. We would say, well, they would say supercomputer back then, but by our standards, it just had a half a megaflop and 4 megabytes of RAM. Nonetheless, they were given the computer to use it for something useful the university wanted to test. And actually use it for numerical simulations of structure formation. And they got very interesting results. And this first comparison came from early 80s, and there was this discussion between globes and chicken. Well, in the East, they also progressed, and then, but of course, following the Zeldovich school, so collapse of the large structure, following the simple perturbation theory, Lagrange perturbation theory. So you see on the left, famous cosmic chicken, basically just a simple kind of a visualization of the few filaments folding together and creating a node of the cosmic web. While the Berkeley group, kind of was getting something like a globes, and maybe the globes sometimes could be connected, depends how you modify the initial fluctuation power spectrum. Finally, also thanks to Jim Peebles, one of his amazing, many more contributions, was that in the mid-80s, there was very influential Jim Peebles paper where he connected the amount of the carbon fluctuations you could expect in CMB with the large structure formation. So basically, we could start to scale the fluctuation, still coming from the observed fluctuation in the nearby universe. This one was starting arbitrary early times. So this means you could start running simulations that meaningfully could try to replicate redshift 0 fluctuations. And they did. And the one of the first famous, I think, applications of those was excluding massive neutrinos from dark matter. The important piece of history here is that in the early 80s, there was this never confirming, effectively, finally rebutted later, result that will come from behind the iron curtain in the is that the Soviets measured the mass of neutrino, and neutrino was massive, and it was like supposedly like 80 EeVs, electron something like that. There was a great risk for Zeldovich because so massive neutrino would be compatible with this largely structured pancake collapse. But so massive neutrinos probably would have problems to create the structure. This is what they believe in the West, and that's what the simulations were done. So here we have CFA, so in the top right circle, have real data from Center for Astrophysics, one of the first extragalactic spectroscopic surveys. And you have 5 mock galaxy catalogs that were produced based on some simple clustering from the simulations run by the people in California. And you have 2 cold dark matter models, some variants of the power spectrum, CDN1 and CDN2, and 3 variants of the hot dark matter, which is massive neutrino models. Obviously, I would say that this looks very bad. I mean, we don't do chi-pi science. You can really use the correlation function to falsify these models, but obviously you see, if you compare with the data, CFA, the clustering has characteristics at different scale, clumpiness is also on different scales, while these 2 models look okay. Well, still, it's just not argument in favor of this model, but definitely, not failing to be compatible with the data is a big argument against the model. So this simulation really helped to falsify cold dark matter massive neutrino model. And I think that was one of the important breaking points when really simulations were proven to be a very powerful and useful tool and had a future in cosmology. And since then, we have been constantly growing in the usage and application of simulations in cosmology. Just to show you that this is really quite become influential field, this is one of the very well-known papers from years 2001, 2005. So we moved 20 years later in time, from 80s to first decade of this century. And it was a paper to Nature showing results of the millennium simulation. First, very, very big simulations that was 10 billion of particles, so quite a breakthrough in many numbers. I mean, then we had some big simulation before, but this level of complication was one of the first ones. And since now the paper is already 3,600 citations, so it's definitely very influential moment. I'm not going to show you the movie. I just show you that the millennium simulation was it's amazing. By the way, it's fully available. You can register on the millennium database and download well, maybe not the particle. For this, you will have to access contact the admins, but you can get the Hello catalogs or many other different products from the database. But I have to show you that when you render the density of redshift 50 and jump the movie to redshift 0, this is how amazingly the complicated structures you can recreate. Now we have a bigger simulation. But I'm bringing up the millennium simulation for a very important reason as well, because now here they had only dark matter particles. I think this is mentioned that something like 20,000 particles. Later you will learn that they're not real particles, but pseudo-particles. When we're going to go to the details how we solve these things in gravity simulations. So obviously, of course, we know that the galaxies are not following the dark matter exactly. The galaxies should be created in some kind of a potential worlds created by dark materials. So these are very simplistic simulations, but I really were quite okay to make this sense because this is large structure. But if you want to start a small scale structure, you need to be better. And that's why the millennium simulation was really nice, because it allowed to create mock galaxy catalogs based on dark matter halos and some informed physical model of how galaxies form in the scale. These models are called semi-annular galaxy formation models. I will tell you a few words about those models at the very end today, in the second part. Nonetheless, here you have pie charts of the extragalactic data. Of course, dots have completely no meaning. They represent galaxies, but if I would plot the dots to the scale, this whole pie chart will be completely white, empty, because we have hundreds of megaparsecs here, and the galaxies are kiloparsec outside. Nonetheless, I dare you to pick a guess which of this. We have 3 surveys: Center for Astrophysics survey, SDSF, Small Digital Sky survey, and 2-degree field galaxy redshift survey. And one color is the real data, and the other color is the mock galaxy catalog made from simulation, a completely artificial fake galaxy catalog that should represent the data. Can you tell which is which? There's no meaning here because I couldn't tell as well. That just illustrated how good the simulation became. Actually, the real data is here, and the red one is the mock simulated data. But nonetheless, you can really, back then, we could really replicate the large structure features of the galaxy clustering but as you know, result of the 14 of billions of years of evolution. So this is, I think for me, this is amazing. And this also shows you that the usefulness of simulations in many respects. Not only can try to understand the process of galactic formation, we can also now much better understand the impact of various systematic effects on your data. Why? Of course, you don't observe all the galaxies. Some of them are too deep and then registered in your telescope. Some of the galaxies are obscure because there are stars, intervening stars from our galaxy, some dust clouds. Some of the galaxies are too close together, so you have to keep two fibers in the telescope and you won't get a spectrum. So there's many effects like that. And of course, they really cripple the data and means that it's not easy to interpret the data. But now you have simulations, and if you are replicating the redshift distributions and sky distribution of galaxies, we can really play around and model all these systematic effects and see what kind of effect it has on its underlying measurement. And this really helps us really combat the systematic effects. This is very important because, as we heard before also in the previous lecture, we're really living now and speeding up in the era of precision cosmology. There will be big data, influence, LSST, Euclid, many more different big galactic surveys will bring so much data for SKA if it happens. In terabytes, petabytes of data, you're going to have millions of validation of particle scale, particle galaxies. So the statistical error will go very small. Definitely 1% is attainable. But if you cannot control systematics, systematic errors is very interesting. This 1% accuracy in statistics doesn't mean anything. So you see this. Being able to make more galactic catalogs is also very interesting. But we also can test it with physics. Like, for example, different modes of dark energy. With making the small catalogs, run simulation with different physics, or maybe different physics with the solar horizon if you want to play with the Hubble tension, and try to see if there should be some effect that you should observe in the galaxy clustering, for example. All right. Okay, so this was about the history, and I think a little bit demonstration that the simulations are a really, really important and very useful tool that we have to help us understand many aspects of this amazing universe we see. And now we have some time before we go for a sleep, hopefully not, to try to discuss what actually we try to do and solve the math, the physics in simulations. So I said before that we're going to focus on gravity only. I'll explain in a moment why. It's not so bad as I think. It might be very useful approximation. But we want to follow the evolution of the and growth of the density perturbations. So you can start the early universe with the linear perturbation theory. Perturbations are small, so linear perturbation theory should hold. So we can define at any place in the universe, at any field or a spatial region, a small fluctuation on top of the smooth pattern. So this will be this rho as a function of time and space. It means this is a fact. This tells you that you have this local fluctuation. It's just a background fluctuation, background density of the universe times a small deviation from the background delta. And this deviation needs to be small, otherwise because now perturbation theory fails. And now, if you define the fluctuation like that, this time evolution of this is just governed by three equations. Continuity equation, and obviously this is mass energy conservation. You see, time derivative of this rho of the density. Any change in time, the local density needs to be accompanied by inflow or outflow of the matter. Otherwise, we'll break mass conservation, energy conservation. So you have a divergence of the product of the rho and the velocity. But you also need to have an Euler equation, which is the balance of energy and momentum. Right? You have a time evolution of the velocity, and this is sourced by gravity, but also pressure. Because in principle, if you want to have a barriers, you will have pressure as well. And finally, you have a quantum equation, which is just self-gravity. Bear in mind, important fact, that in the general theory regime, gravity is irrotational. That's why the rotation of the phi, which is the potential, should match. And the Laplacian of the potential is served by just the density fluctuations. You can solve this quite easy, and you can find all the simple steps in the lecture notes I sourced at the beginning. Basically, what you do, you just think about the perturbation series, you know the perturbation are small, you can plug after some dimensions one equation to the others, and then you just throw away all the terms that are like the delta square or higher, because the definitely will be very small. So you neglect them, so that's just a classical perturbation theory. And then moving also from the proper units to moving units, you arrive at the evolution density equation that we have here at the bottom right. And now, before we try solving this, and let's explain what the terms are, we need to get used. We can really use one of the nice properties that in Fourier space everything usually is easier. So we should move to new Fourier space, and we can do this because in the early times the density of waves of different size evolve independently. So you can find really basis of polynomial vectors to describe the whole density field. Therefore, you can allow us to basically describe local real space density field as a Fourier series, right? So this is the classical summation with this discrete Fourier, not continuous transformation. And of course, this is great because in Fourier space, differentiation becomes a multiplication, right? So you have here, you know, the first derivative is just minus by k, and then the second derivative is just multiplied by k. This is how the math tells us. So if you do this, then you arrive at a new simplified equation for the evolution in time of the density perturbations in Fourier space. That reads like this. So here you have hydrodynamical. So this is just a piece where the background expansion of the universe enters. Because this is already just a set when we use Newtonian gravity in an expanding background. So there's no real GR. GR is just a Fourier equation that solves separately, that gives you the evolution of the scale factor of the universe. The Hellwing, as you can see, is just next to the first sign derivative. It just basically tells you that when the universe expands, the whole fluctuations should be smoothed out. Either they are negative, like in cosmic voids, or positive. This is like something we call a Hellwing. But the most important factor here is on next here is the source term. This is what sources the time evolution of the density perturbations. This is in parentheses. CS is the sound speed, and rho zero is the background density, and this is multiplied by the local Fourier local density. Okay, so this is the second order ordinary differential equation that's very easy to solve. This is piece of standard curriculum of, I don't know, second year cosmology, astronomical, third year maybe. Well, you can do this. I've heard that most computer scientists and people that are not physicists by training on this audience, so I will just very quickly tell you this is very easily solvable after the simple assumptions. Of course, you need to have the input from external equation, which is the Friedmann equation to the universe. When you fill your universe with all these components like radiation, matter, dark energy, and then you have a kind of evolution of the scale factor of the state. Once you have this, you can solve this for various epochs, and we focus here on the example matter domination epoch, because this is the epoch when the matter dominates in the Friedmann equation, dominates the dynamical evolution of the background universe. And this is the only epoch in the different universe that was quite long, when the structures can grow actually efficiently. During the radiation domination era, you know, the radiation pressure was too high, so in environment the fluctuation couldn't go at all. John in the previous lecture described this, because the Thomson scattering of couples plasma to photons, they could at best oscillate, but the dark matter could only grow at logarithmic, so very slow. It's a some growth, very slow. But after the coupling, matter dominates and can really effectively form the structures for the next 80 millions of years to come. But now if you look at the system in the parentheses, so the state of a given density perturbation described as delta k, some k with a vector scale, depends on the sign of this source term. So if pressure is bigger than the self-gravity, so if this inequality holds, we have solutions that are periodic sinusoids in time. The fluctuation is oscillate. Well, if you have a pressure rise fluid, of course, gravity acts as a compression force, but the pressure grows as it compresses, and the pressure starts acting like a restoration, like a harmonic oscillator. So there's no structure formation, and that's what you rate. But when you have a regime in which self-gravity dominates when this fails, the pressure is either zero over matter or it's much smaller than the self-gravity, which is also true for vacuums and a lot of structure. Because the vacuum gas have very high pressure if you start to compress the clouds to stellar like scales. But on scales, on galaxies and largest, the pressure is too small compared to self-gravity, so you can also form transport gas on large scales. And they have a growing mode solution and leads to collapse and formation of structure. And there's also a bond diagram of exactly the pressure equals self-gravity between these two regimes. And this is very useful because whenever you find this at given epoch of the history of evolution, this bond diagram, you can find a minimum characteristic mass of fluctuation that can start to collapse under its own self-gravity. This is called genius mass. So, yeah, so we describe how the structure is formed. Okay, lecture is finished. We'll see the coffee. Or did we? No, of course not. Of course not. But we have in the core. Why? Because this is linear perturbation theory. We said all these equations were solvable because we neglected all the terms that are higher order than the first. And of course, once the gravity starts to collapse, you start to grow the density contrast, and the delta, which is the kind of local deviation from the uniform vacuum, becomes larger. As soon as it becomes comparable to unity, or even worse, as soon as it no longer much smaller than the unity, you're no longer allowed to throw away these higher order terms because they start to be big and contribute to the equations. So, in modern day, as I said, in centers of the galaxy clusters, you can get this delta of medium, 10 to the 6. So of course, we didn't solve the problem. We just showed that it's possible to do this for large scales or really times. And to show you what's the difference between these two, by the way, finally I will show you how quickly maybe such plots are maybe not so great for doing the brilliant visualization, but they are very good to get some understanding. So on the left is the density approaching zero of Earth simple simulation. Maybe you will, if you like, you can run such a simulation, well, you with me, if you follow on Friday. Approaching zero, you see deltas are density has much larger than unity, nearly everywhere. Even in cosmic voids, the delta is close to -1. -1 is, if you take absolute value, it's comparable to unity, so it's an regime. And now on the right-hand side, I smoothed the density field using a top-cut smoothing or Gaussian smoothing to get the density contrast values again below unity. So see, you can't understand the left picture if you only allow to have a density contrast like on the right picture. This is the best you can do with the linear perturbation theory. So, well, of course, simulations are needed and we can solve the problem. So, a few words about the setup of computer simulations. Then, unless there are any questions in this first part, now we will become a little bit more technical. Okay. Hopefully everything was digestible. Well, first of all, I was able to show you that some of the simple methods that we use in computer simulations are really easy algorithms that you probably can sit down and write home particle mesh code. We'll describe this later in a few days' time. Of course, this is a good exercise if you're especially doing the programming and you want to understand what is happening in the simulation. But if you really want to run this big random science simulation, you don't need to do this because many other people did this for us. They were dedicated, borrow computer science, borrow new algorithms from computer science. It's not only about solving gravity, density, and expanding vacuum, it's also about handling the huge memory issues and computations. There are plenty of code available now, and they are open source and relatively easy to compile, even on your laptop. If you have a Linux or Unix system, you don't need to go to supercomputers right away. And you can even set up simple small simulations because most of the codes listed here come with some kind of startup packages. This is maybe not most up to date, by the way, this, but just to tell you that there are many different things. And some of the codes use different methods. And I will try to cover now not in the next 40 minutes, but also after the break, slowly, some of the basic different methods and what they are different. So you may be later, if you see go at our web page, you see string in mesh code, you will understand what your limits it has. So if you want to take rounders, for example, you will know it's a adaptive mesh requirement, you also have different limitations. But most of the methods part that will be covered in the next part is based on the gadget code. First of all, because I have the most experience with the gadget code, like Wojtek Hellwing. Second of all, because now, finally, after 15 years being overdue, we have Gadget 4 public version. There was a 15 years gap, interesting, between the Gadget 2 release, which is 2005, and 2020 Gadget 4 release, when you have hundreds of papers that says we use Gadget 3 code, which is unpublic version of the public available Gadget 2 code. So actually, nobody knows what this Gadget 3 is. You could get a Gadget 3 copy if you ask, but there were so many different copies of Gadget 3. So it's good that we have also, again, the public version that can be understood and tested by everybody. And Gadget is relatively well spread and easy code to use. I don't think it's normally the fastest code. I will put my money on the Swift, but it's definitely very widely used, and you can download Gadget 4 for yourself and play with it and run simulations. And if you understand how Gadget works, you definitely will have a better understanding of how all these other codes works as well. Okay, well, so pros and cons for different languages. This is also something I want to cover before we start discussing, because all these codes were written in different computer languages. And basically, I think it's, I will agree, this is the slide borrowed from Wojtek's finger, I think, where if you really go through list of the good codes, efficient codes that are being used widely because they produce good results in a good amount of time, they are only written in 3 modern languages. So first will be C, and I listed some pros and cons of this language in writing this language. This is just a slide to show if you want to get into the details, if you want to modify the code yourself. Because all the codes you will find are probably designed just to make a simulation of the vanilla numbers in here. If you would say would like to sit down and study different dark energy model or some other exotic physics, probably you will have to modify the code yourself. So you will have to understand the language which the code is written. So C is particularly fast language, is highly portable. It's a subset of C++, if you would later want to extend to C++. It's very powerful, low operation of bits, so it can be very fast. It has a very fast I/O operation. But it also has very important and significant drawbacks. There's no runtime library for automatic input-output errors. No RI bound checks, easy to write code that was segmentation fault. And trust me, I think this is the the compiler result that I've seen most time in my life, segmentation fault, right? Like you write the code, you think it's all right. So it's also hard to debug. Yet, it gives you this power that will be probably, if you finally get rid of the most important bugs, you're going to have a very, very fast piece of code with the access to direct memory. That's important. I mean, more important. One was not 77, but important 95, for example. Easy to learn. Runtime library helps you tracking down many of the problems of I/O. The large body of legacy code, because many of our masters from 80s actually code this in Fortran 77, so there's some connection. Well, compilers, fast compilers are mostly proprietary and buggy because there's not so big user base. Word syntax is very anachronistic, and there's a restriction of the source code. And this is a bit of the dying language. I don't know if many people would agree, because Fortran 95 is actually quite fast language. But if you would like to think that, involving into learning prompt coding is something that is really good for you. So, and you might later use it also outside academia, because not everyone will stay in academia. Also inside academia as well. You might as well learn modern language, not the dying. Finally, the C++, I would say, which is the youngest of these 3 languages, is it's kind of a object-oriented version. people tend to say of C, but C++ is actually a separate language. It shares the syntax with C, but philosophy of programming in C++ is different. Because an object, you can build complicated, large body of code that is easy to maintain, much easier than C. Second language is difficult, by the way, to learn, unfortunately, and often can provide, because of these overheads, this whole objective nature provides overheads in performance. Now, where's the Python? Because I would assume that most of you probably use Python every day. Python is a very powerful language and simple to use, mostly for data science. It's very good to use Python to analyze the data, very good to use Python to visualize the data, very, I think, good and useful to use Python to do simple, like, let's say, perturbation theory calculation. But I didn't have Python here because until recently there was no code in Python, I know, to do n-body simulation, and that would be actually reasonable. And this, I have a good information for you. For all of those of you that love Python and would like to learn the C, now we have to fill this gap. We have something that has been called concept. It's a new thing from this year. Apparently, there's an n-body simulation code that has been written in Python, but it uses something that's called Cython. And the authors claims that it achieves C-like performance. So if you like playing around with Python, here's the link for you. You can download the code from the GitHub and also try to learn concept. I'm not sure if this is really that much competitive, but definitely there's a code paper to this code, and I've seen this is the work performance test that wasn't that bad, actually quite good with some number of cores, but I'm not sure. I don't have experience with that, so I don't cover it. Nonetheless, if you prefer Python, now there's an option to do this also in Python as well. But you can see it's a little bit cheating because there has to be some C library to speed up. That's why I think this Python. Okay, so I said I will focus on gadget 2, which is sometimes also portable to some of the methods from gadget 4. But the methods for solving the problem of structured information that I will cover here just briefly, quite universal, but also go beyond this particular code setup, because it's just a kind of numerical approach to solving force and plasma and gravity equations in a computer. So the problem that we want to hit, that we have at hand, consists of following as precise as possible 40 of years of the mass fluctuations evolution, but not only mass, but also velocity, so that it comes for free. So there are a couple of different approaches. I will cover this here too, but I will mention also the third one, which is something like a hybrid method. So first, you can discretize space of your domain. It's an Eulerian approach. Then you represent the state of the fluid on the mesh, and you have volume elements in this mesh. Advantages: very high accuracy for shock capturing. If you have a high frequency pressure, entropy, grid codes are very good for that. And low numerical viscosity. This is if you really would be into hydrodynamics. The other method is Lagrangian approach, when you don't discretize space, rather discretize mass. This means that you have these particles, but actually pseudo-particles, that represent fluid elements, actually phase space of the fluid elements. And we call them particles for simplicity. And these particles basically trace the elements of the phase space, and then they move under the gravity. And the principal advantage is that because now the mass elements are represented by some particles that have position coordinates, whenever you have clustering, more mass accumulates, you have more of the particles there. So kind of a resolution of the mass adjusts itself naturally to the clustering. In Eulerian, just if you have one grid, basically you never have the same resolution. You can try to get away with that if you use multiple grids, but in principle, Lagrangian approach allows you to just automatically adjust the resolution to the flow, to the clustering. And I said I'm going to mention the third way, which is the kind of a small branch that's growing in the last 10 years, which is like phase space integrators that try to integrate the phase space directly. What this means will become apparent as soon as we describe the problem in the equation. So the simplest scenario we have is covered with just the dark matter. But they will use commonly dark matter only simulation, but I think the proper name is gravity only simulation, because we still have this 4.5% of total energy density of the universe in form of baryons, but we just neglect that the baryons have pressure, the baryons can radiate, we just treat these baryons as dark matter. So people simplify things saying this is dark matter only simulation, but essentially they're just gravity only simulation. And these are motivated by the fact that 85% of the total matter in our universe is form of the dark matter, according to the standard model. And the dark matter, according to this model as well, just really cares about gravity, maybe weak forces, but they are negligible when it comes to structure formation. So basically, you can use gravity only approach. This means you ignore all the hydromagnetic atomic physics connected to the baryons and model them as collision is fluid. So there's a limitation, but there's a huge advantage, because this approach tells you that we only model gravity, and all the physics is kept as simple as possible. So there's no many ways when you can really do strange things by simplifying all this complicated gas physics in a different way. By the way, that's a completely different story. As I said, hydrodynamical simulation will require a separate dedicated school of 2 weeks at least, because it becomes so complicated field. The problem is, remember that we don't observe dark matter. So as long as we bear this in mind, we'll remember what's the usefulness of gravity on the simulation. And there are plenty for useful. We'll see also on Friday how we can really even study and falsify some dark matter models just using dark matter on simulations. But basically, in that picture, that's a rendering of the dark matter and the stellar light predicted by the full hydrodynamical simulation from the Apostle simulations, courtesy of my colleague Till Savala. So I will show you here that in the upper left part, I'm waiting because there's some delay, I think. Okay, you have a dark matter. So if the dark matter would shine, this is how we should see. This, by the way, this is simulations of the local group AMO. So in the center, you have two big galaxies, two big dark matter halos. One is supposed to be Milky Way, the other should be Andromeda, and some Magellanic clouds. So you see, the dark matter simulations predict there's plenty of fluctuation, this clumps and halos and subhalos everywhere. But now the same simulation run full height of the galaxy formation, follows star formation, all this physics, predict that stars are only visible in a couple of the biggest halos. We can try to understand why is this the case a bit later, but just bear in mind, right? So the universe we're going to model in the gravity only simulation is this one, and the universe we observe is this one. But as long as we can make meaningful connection between those poles, we can still learn plenty of things. Okay. So I think I should make a break at 4, right?
Yes.
So another deep breath before we go to some math. Hopefully not very complicated. So we try to solve this self-gravitating fluid in expanding universe. And because in principle we believe there's a dark matter, particle, atomic level, dark matter, particle level, there's so many dark matter particles that we can approximate them using single particle distribution function, which is just given here. So it's a function of the phase space distribution, occupancy of the various states of this dark matter fluid. So it depends on time, of course, position and velocity. It's a phase space function. And because there are so many dark matter particles, using this we can really they shouldn't scatter locally if this is real dark matter physics. So they should only feel mutual gravity. So this tells you that you will deal with something we call quadrant-Blasov system in the gravity-only simulation. So first we have a collisionless Boltzmann equation. That's the evolution of equation of the collisionless particle fluid, of single particle fluid, so there's no interaction between particles, right? So we have a time evolution of this distribution function, and then that depends on well, there's a gravity here, of course, because you have a partial difference of the potential. And of course, you put the different phase space elements as well. So actually, the phase space elements we're going to call characteristics. They are particle orbits, and the phase space is always conserved along the particle orbit, which is called characteristic of this equation. But you also need to solve, of course, quantum equation to generate self-gravity, and this is this part. And for the first time, I think I give it here this in the integral form, not in the differential form. Very simple Laplacian of the potential is just corresponding to the it's responding to the fluctuations of the distribution of the density. All right, and this basically tells you that you can use the fact that the phase space is conserved along the characteristic, and just you can use these particles that you throw into your computations as a Monte Carlo traces of the underlying smooth phase space for dark matter. As long as we remember this is the Monte Carlo traces, and we'll be leaving because of that, we should be safe. So this means, like, if you recall from your, I guess, conditional algebra courses, well, okay, let me ask differently. Who of you, at least once, did the numerical integration of a function using Monte Carlo approach? Okay, I see some hands. But in essence, basically, Monte Carlo is just like, well, name comes from the famous Dutch in Europe. So plenty of people playing roulette, poker, and all these things, harder, guessing and playing the risk chance game, chance. So in Monte Carlo approach, for example, right? Let's say you shoot to a target. Target has some shape, right? And let's say you shoot thousands of bullets, and then the bullets cannot go above some, let's say, rectangular. And then you say, okay, I hit under my target 30% of bullets, and 70% of bullets were also. And you can use this fraction to approximate the surface area of the target. We here cast thousands of pseudo-particles because in the Monte Carlo way, they probe the underlying phase space. But this means that locally, because there are just chance in the Monte Carlo, there will be this intrinsic noise. And that's always going to have a problem with resolution, and you're not really fully solving the Wasserman equation, you just approximate the solution. But you can live with it. And there's amazing science that can be done even with this. So okay, in this Monte Carlo approach, if you now go down and then break down the Wasserman to the sense that you have particles that are tracing the underlying fluid, you need to solve this equation. So first, it's just the equation of motion, right? This is second order laws of Newtonian dynamics. So force is the gradient of the potential, minus gradient of the potential of the particle. And the other equation is just the particle discrete version of the Poisson equation. The potential is just the corresponding distribution of the particles in the particle law. So nothing really new here and special. This is already casted in the way that all this expanding universe is not visible here because x is a co-moving coordinate. So cos usually integrate equation of motion and so gravity either in co-moving or even in super co-moving coordinates. They make all the equation transformations so they work with unitless equations because it's much simpler. And all the extension, kind of like co-moving frame of the universe happens in the background level. But then at some point, of course, you need to recall that if you compute the physical forces. So bear in mind that it's all in co-moving coordinates, so the extension of the universe is kind of hidden. The important thing is that even if you have just 5 or 100 particles and you sit down, you draw these particles on a sheet of paper, you assign mass to these particles, and you solve the equation just hand by hand. You can do this. With 100 particles, it will take more than half an hour, maybe, or maybe 1 hour. You will have not able to compute the forces precisely, infinitely precisely, because you need to introduce this small epsilon parameter. Why? Because you have collisionless fluid. And in principle, you could have some 2 clumps of dark matter being orbiting or just floating in the same region of space from opposite directions, because they are collisionless. This means that at some arbitrary point of time, you can find these two particles exactly at the same position. They have different velocities. They will, of course, influence somehow gravitationally, but if you don't add this epsilon, you will immediately obtain infinite force, infinite potential. And the particle will explode or just get very arbitrary high velocities. So because we use this Monte Carlo approach, we have to remember that, and we add this epsilon, which is called force softening parameter, that assures that at small scales, these two body particle interactions do not break down our momentum an equation of motion approximation. But this also means that all the simulations will be always limited, even if you have many, many particles, to the fundamental small-scale force resolution given by this parameter. So not only mass is limited by the number of how many particles and what the size of the universe you model, but also the force, spatial resolution of the simulation, because you need to introduce this epsilon. Okay, so the dynamics of structure formation, as I think I convinced you, is mostly driven by gravity, and we're going to focus on gravity. So gravity, that's a big thing. Well, we know that gravity is described by general relativity, and we should be smart, we should do general relativity equation. But in the context of the large structure, it's been shown many, many times, among others also GP, but many more different authors, that relativistic corrections to large structure clustering are very, very small. So you don't make a big mistake if you do the non-relativistic approach, which is basically you do Newtonian gravity in expanding background. And this is what we all do in the simulations, except some of the simulations that were simulation codes and approaches that were produced and created by some of the groups. I think I'm calling this Julian Adamek from Switzerland, Verdurer, and Thomas Buchert as well. When they wanted to really do this also full GR, or not full GR, but some of the more GR-like geodesic calculations. And they are very interesting, but they actually prove the concept. The corrections to the GR full treatment are 10 to minus 6 at best in some cases, which are well below the resolution of the simulation for most of the cases. But not for all the cases, because of course, if you start to put black holes in your simulation, you have to be careful, right? Maybe in central galaxies, the black holes shouldn't just give Newtonian potential. It will be wrong. So dark matter is collisionless. It simplifies, I think, that we have this Monte Carlo approach to n-body system. This means that if you have n particles that sample in your piece of the universe, the underlying dark matter fluid, you have 3 times n coupled nonlinear differential equation of second order, right? You have this tells you that we have this simplified. Sorry, too much. There's a delay on the Zoom. Okay. Yeah, so this tells you that you have at least 3, because also there's a 3 directions, right? So in general, this means that you have a big problem. Wait for the switch. You have 3 times n coupled nonlinear differential equations, very hard to solve. N is very large, and in principle, all equations are coupled to each other. This means that actually, in all practical sense, this is really an unsolvable problem if you live like that. If you want to go really many particles. On top of this, you would like to have hydro. Well, this I'm just mentioning this because, of course, hydrodynamical is important if you want to study galactic formation in the cosmological context, cosmic web. So you need to capture shock waves, radiation process, have a star formation, supernovae, when the star forms, black holes, etc., etc. So this is a separate piece, and you know, if you are already wasting too much time on gravity, there's no chance, no hope that you will have enough computer time to add hydrodynamics. So let's make the gravity solver as simple as possible and as fast as possible, so that we can use all these extra resources to study this interesting gas process. And if you look at this, then you immediately understand that you have 2 conflicting, racing against each other requirements if you want to study structure formation using n-body simulation. Because the dynamical range of this is so huge. 14 billions of years, 11 orders of magnitude in density contrast, you know, a huge volume as well. And what are these problems? So we want small particle mass to resolve internal structures, halos and galaxies, right? So this means that Well, you also want to have a large volume, right? Why? Because you want to model representative piece of portion of the universe. Well, it's still going to be ensemble averaging. You just take a randomization, but you just don't want to study some small part of the universe if you want to make a simulation that later will be able to give you one galaxy catalog of SDSS or Euclid, for example, right? Well, this means that you need very, very large number of particles. And because you want all the particles to have a small mass, so as more particles you add, the particles, individual particle mass goes up, because they just represent some of the smaller pieces of the background density. But if you increase the volume, you even more multiply the number of particles. So these are raised against each other. Because obviously the computer memory is not infinite. And also you don't have a lot of time to waste in the CPU cycles all these n particles. So you might be tempted, maybe I'm going to do 100 small boxes, right? So at the same time, I have good physics, good resolution, also some representation. Well, there's a problem with this approach because as soon as fundamental modes, the largest perturbation you can fit in the box, goes non-linear. And this usually happens for small boxes when the first Halo form, the simulation cannot be continued before that point because it's become non-physical. So basically, sometimes in the literature you will find that some of the simulations were run to redshift 2 in a small box because they wanted to study random alpha or high redshift universe, but they couldn't carry on the simulation to lower redshift because the box was too small and there were throwing too much fluctuations inside, like 10 megaparsec box, 20 megaparsec box, things like that. But also, you're never going to get very complex. Even if you have 100 small boxes, you're never going to get very complex because the very complex usually reflect the combination of much larger scales. Like very big voids, cosmic voids, happen very rarely. Very big rich clusters also happen very rarely. So if you cannot squeeze enough density fluctuation in a small box, you will never create rare voids and rich clusters. No matter how many hundred small boxes you're gonna how many hundreds of small boxes you're going to take. And, well, of course, you might say, okay, I'm going to take a big box, but I have only 1 terabyte of RAM, so I can fit maybe 2 billion of particles. Okay. Well, so my particles will have a large mass. So, well, the problem is, because it's Monte Carlo, right? The more traces you use, the more precise your simulation. So if you want to measure mass of Milky Way halo, which is let's say 10 to the 12, but your particle mass in simulation is 10 to 11, it means you only have 10 particles per Milky Way halo. And this is random process, it's Monte Carlo. You by chance might miss 2 particles, and then you will say the mass of Milky Way halo is 20% lower. Or you might add 5 particles by just random chance. It's shooting thing. So this means you won't be able to resolve physics if you go close to the particle mass limit. So small galaxies are also missed because of that. Okay. So you have to bear in mind that you always need to compromise, and that's why cosmologists are one of the rare species that will always take up the whole computer if they're given. That's why we kind of visualize the Cordon process in supercomputers. But for example, many physical particle physics problems can just need to run the same small simulation but hundreds of thousands of times. Okay, so they can really know, they would like to speed up, they can, let's say they use 1,000 CPUs, they can wait a week or a month or even half a year, but they can wait. We cannot. We want to do as many particles as possible, as big blocks as possible, which means you cannot just really split this into smaller pieces. So there's always this compromise you need to make, and that's why cosmologists are the people that will always try to take the biggest computer available on the planet, if they're given the chance. Okay, the most important question that before you start designing and running simulations and which code, which method you pick is that how you can compute forces efficiently, but also accurately, right? Obviously, efficiency, accuracy, there's another trade-offs. You might simplify the forces on some larger scales, then you're going to compute them very cheaply, but they're not so accurate, right? So it always bear in mind what you want to start. If you want to start large structure, cosmic web, let's say how many times big voids create, something like that. Like you may heard, maybe you heard from Lynn Biker. lectures, maybe you don't need a big mass resolution when you can get away with the relatively big box, but smaller part. But if you want to study in small courses, but if you want to study managing of some chaos, smaller than Magellanic clouds in the local group, you definitely need much more precise forces, but maybe you don't need such a large volume. How do we integrate the equations of motions, like orbital equations of motions in time? We need to progress the particles in time as soon as we get forces, and it is also not a trivial thing to do. And finally, how do we generate appropriate initial conditions? There are many ways, and I will cover something today that's called Zeldovich approximation, because I already brought Jakub Zeldovich, which is a very simple procedure that gives you reasonably good initial conditions that are good for toy models. I mean, we used very prevalently 80s, 90s, 2000s. Now we use usually second order Lagrange perturbation theory, which is much better and allows you to start simulation also at lower redshift, which means you save some time. But you need initial conditions, then you need to compute forces in the simulation and then integrate this in time. These are basically three main things that all computer simulation software should have. So if you go back to these equations and you throw some particles in the box and you want to solve them explicitly, this naive that tells you that you need to n-square calculations of forces and potentials. Right? So for thousand particles, already million calculations just for one time. Right? Well, for billion, you have 10 to the 18. So this is impossible. Obviously, naively you cannot use this. So we need to be smart. And I'm not that smart, but I borrow some of the wisdom from smarter people, because this field has been developed for 40 years. And I will show you how we can smartly introduce quite a simple algorithm to get reasonably good accurate forces and reasonably fast computations without lose of so much of the accuracy. And I think I will start discussing these methods after the coffee break, leaving some small time for the questions. Thank you very much.
Thank you. Any questions? Hello, thank you very much for the talk. I am wondering, what's your opinion regarding the dwarf galaxy problem, which a lot of simulation struggles on?
Which one? Because there are many.
Yes, so for instance, the one that predicts that there should be many more satellites, galaxies, but we cannot observe them, for instance, for the Milky Way.
Very, very good questions. It's been known in the literature as a missing satellite problem. It's brought by Tori Kippin and Andrew Kraft and Moore as well for the first time in the late 90s. So it's interesting that first simulations were very simple, and we couldn't afford that many particles. I didn't cover the algorithm, but nonetheless, imagine that we already understand that you have this racing argument that you want to have big volume, but also as many particles as possible. Those simulations couldn't afford them in the 90s, so they necessarily had a high particle mass, and there were no satellites first. So first, there was no satellites in simulation problem, and the satellites observed. So people thinking, what the hell is happening? Well, but most of us suspected, well, most of people suspected that if we increase simulations, the proper physics will kick in, and then you will find these small structures. Indeed, this is what happened. We increased simulation resolution. All of a sudden, all this cloud appeared, but then we went to this problem, right? Which is the nearly there. Yeah, done, right? That, okay, please give it a moment because it's on Zoom. The picture I was showing you, yes. So, yeah, you had so many clouds of dark matter, and yet there's no, well, this is simulation, but imagine that, let's say we observe this, what is on the black part of this box. And then everyone says, well, where are the satellites? Now we see all of the satellites in simulations. And a Milky Way halo, back then when we finally made the proper resolution, we were expected to contain 600 satellites that should have some galaxies, because there was just all 10 to the 8 solar masses. Yet we knew back then like 20 satellites, right? That was a big problem. But then again, the solution came with the fact that we ignored some of the physics. There was gravity on this simulation. And now it's important to understand that it's not so easy to make galaxies in our universe if you have small cloud of dark matter. This is because of the re-ionization epoch, the time when the first stars that came after the Big Bang produced so much UV radiation that it ionized again the neutral hydrogen, basically heating up all the intergalactic gas to around 10,000 kelvins. This means that if you were too shallow of potential, let's say we were 10 to the 8 solar masses cloud of dark matter, you couldn't retain this hot gas. You have too little gravity, and this hot gas would flow away. This hot gas later would come to the much bigger guys, like Milky Way here. No? Eventually, this hot gas, because it's radiating away energy, cools down. And of course, when it cools down in the big halos, if you are small halos and you lost in gas, you lost forever, because without gas, you can't form stars. So that was the missing piece of information of physics, by the way, related to binary physics, why we now understand that not in all of the small planets there should be galaxies. So we resolve this problem of the missing satellite by understanding binary physics. But again, it's interesting that before missing satellite was too many satellites observed. So it's always bear in mind that the simulations are only simplified way to model the universe. I think I answered your question. Maybe later I will comment, because now we have also more galaxy problems, but they are different ones. We have the internal kinematic properties of the profile, the density profile.
Thank you.
Another question, but a comment. I heard before tournament dialect, and I think a good reason why it works is the high-level languages. It's much the most similar in syntax to Python. So Python maybe put it on last for it.
Thank you very much for that comment. As I said in passing that not everyone will agree, and I think there was this part of the maybe in the 2000s and 2011, 12, it certainly looked this way. But indeed, I agree with you fully now. The Fortran is back with the vigor to the scene, because, as I said, it's syntax is very easy to learn, and it's now been also implemented the high-level languages.
Okay, so I would have some questions to you. You are talking about the simulations in cube, right? What about the boundary conditions? How you treat the boundaries of the cube?
Well, so I didn't go to that point yet, but basically,
But you will, right?
I will, yes.
Okay, so
Most of the simulations we do are very periodic numerical conditions. So basically, that's why, by the way, it's the problem that you don't have all the missing nodes, because you don't have nodes on the given box. But you replicate the box on all the edges. So it sits
but also it creates another point of concern that naively, purely periodic boundary conditions reduces you to the toroidal topology. So you should avoid this by tiling periodically in infinite universe. Okay, but as you promised, it will be touched upon next.
Yes.
And my next question is concerning the Blasov equations. You've seen that the only modification from the GR is the expansion. You work in moving coordinate and expansion. How about velocities in the Blasov equation, and how you treat properly the expansion on velocities?
So
in other words, on if we're working in space.
Yeah. So as I said, no, this is only addressed exact by the phase-space solvers, try to solve the puzzle system. In Monte Carlo approach, usually with the transformation that we follow the momentum field, And because of this, basically, you basically don't follow physical processes, but technological processes. So you're kind of a decouple, the background.
Okay.
So it's not fully strict, of course, I agree.
Thank you.